Hello, this is Dr. Mike with a quick demo of NumPy within the Jupyter Notebook. So far in Python in the class, we've looked at Python as a series of commands, loops, logics, variables, and so on, ways to import and work with data. NumPy is going to be our first core library. A library is just a set of functions you import. And NumPy being probably the primary scientific computing library that's seen for working with something called arrays. So arrays are just grids of values, usually all the same type. So I can't have an array of name Mike and then a number 10 and then a 1.25 float, for example. They have to be all the same number. They are indexed automatically by a tuple of non-negative integers, and they all start at 0. So example, column 0, row 0, element 0, and so on. So to start off, real simple, is we're going to import the library. Probably the most common thing we're going to see is import statement, and of course the NumPy library, and they're going to say as. We're going to use this NP as a way to identify it in the rest of the notebook. So it ran. If you want to double check, you can always say np.version. You can see I've imported NumPy. Is been imported from my local versions.py. So let's look at our simple array here. So let's build a simple array. So the very first kind of look at it is the np.array command. In this case, we're going to create one called A. And now we can basically print the type of A and print A itself. So in this case, it is a class of the data type. We've seen types before. You can do the type command to see is it an integer, is it a float. In this case, it's an ND array. It's a very special data type. And we get the output here. It's 1, 2, 3. So it's a rank 1 array, which means basically one row. Again, we can work with more than one rank. So in this case, we're going to create an NP array. Again, np.array is our main command. Here we're going to create an array called B. So B equals np.array. And notice the syntax here. We have a start and ending parentheses. Then we have a start and ending bracket for the entire value of arrays, all of our ranks. And then we have a start and ending bracket for each rank, with a comma splitting the ranks themselves. So here we have 4, 5, 6, 7, 8, 9. I'm going to create a rank 2 array. Here we printed B out. Rank 2, think about the rank as the number of columns. So it's got 2 columns. This is usually called a shape. So here we can see the shape. If we do b.shape, actually it'll tell us it's a 2 by 3. So 2 columns by 2 rows by 3 columns. Excuse me. And usually each one of these individual items is called an element. So we can call this a column. We can call this a row, very similar to a spreadsheet. The .shape command will tell us how the shape of the current array is. So in this case, b is 2.3 is 2 by 3. So again, we've been creating these with just random variables here. I've been typing in 4, 5, 6, 7, 8, 9. But we can create one with just zeros. So here we're going to create a 2 by 2. Notice the syntax again. In this case, there's no brackets, only parentheses. And it's double parentheses here. So we're going to create one called C, which is nothing but zeros, and is a 2 by 2. So the shape is 2 by 2, right? 2 columns, 2 rows, 4 elements total here. Or we can do np.ones. We want to create a bunch of ones. Or we want to create an array with .full, which means for a full array. In this case, we're going to actually, of course, give it the shape 4 by 4. So we're going to set a 4 by 4 shape array here. We're actually going to fill it full of 7s. So lucky number 7, right? Here we go. 4 columns, 4 rows. Again, everything starts at 0. So this would be 0, 0. And of course, we can actually just say random numbers. And yes, it's not a typo. It's a np random.random. And again, double brackets there, double parentheses. And we create an array of random numbers. So I'm going to create this multi-rank array here called G for further processing. So let's go and use this in something called slicing. So again, everything here is indexed. I mentioned before, this would be 0, 0, and so on. So it's 0, and of course 1, and 2, and so on. So we can actually go with an array here. Using the index that's provided by NumPy, we can slice out parts of an array. So this example here, we sliced out the first 2 rows and columns 1 ending at 3. So columns 1, so again we start at 2, and then we end at 3, so we get these 2. And we get the first 2 rows. So 2, 3, 6, 7. So we've sort of sliced out this part of this array. So from G, we sliced out into F a new array, a new simple 2 by 2 there. So again, it's called slicing. Again, we can look at G again here, and we can actually say go again and get row 0 element 1, row 0 element 1, so row 0 is the first element, and we get, first element, right? Start at 0, right? This would be 0, 0, so 0, 1 would be number 2. You can see we got 2. So here we say from G get 0, 1. Very simple. We can again slice out individual elements, slice out sections. And then beyond that too, we can actually replace elements. So again, let's run G here. We print G out. Again, G's are 1 through 12. In this case, we say take element 0, 0, which we know is 1, and replace that, or that equals to 77. Now we print G again, and you can see here it's been replaced with 77. So we can go in, pull out parts, we can replace elements, create new arrays with parts of the larger arrays with slicing. So slicing is a great way to go and take parts of a larger object. Now we have the shape again. We have the shape here. Again, G was a 3 by 4, 3 rows, 4 columns. And again, it was the 77 was 2, 3, 4, and so on to 12. So we can use the G.reshape in this case, or .reshape. G is just our name we gave it. And we're going to create a new one called H. H is going to equal G, which is this array. And we're going to make it a 12, just 12. So you notice the comma. Usually you can say 12 by 2, 12, or whatever makes sense here. 12, 6 by 2, and so on. You leave it blank after the comma. It did denote 0. That means just 12 across. So we create a single rank array of 12 elements. So again, we can reshape arrays, slice them, dice them the way you like. Again, a quick note. Let's look at G again here. G is this array right here we've been playing with. It is an array of elements. So you wonder what kind of elements are these? So there's actually something called D type. Earlier on we looked at if you do type G, you'll say it's an ND array. But you wonder what actually is the elements inside this array. These are integer 64s. When we create arrays, work with them, we can actually do the D type equals. In this case, we're going to create a NumPy array 1, and it's going to be a NumPy array which equals 1.53 and 2.32, and it's going to be a float 64, which is our decimal. And you can see here we now have an array of 1.53 and 2.32. And we can see the types here are float 64s. So we're not bound to just integers, so we can work with float values. And this can be very powerful when you work with very large floats for precision measurements, for example, and things you can compute on. So, array math. It's probably one of the greatest parts of here is here we have a simple array. It's going to create an array of float 64s here. So 3.33 and 4.4. Again, these are D types of float 64s. Now, how can we add arrays together? So remember, we have NA1 here, which we created. Let's go and run this here. Here we have NA1, which is at 1.53 and 2.32. And we created this one here, 3.33 and 4.44. And a simple addition. Now I could say NAX equals NA1 plus NA2. In this case, I'm just printing them across, just printing the addition. But that's it. You just NA1 plus NA2. Very simple. Same with subtraction. We just say NA2 minus NA1. So we can do it in different orders here. You can see everything is done down here, right? So in this case with the addition, it's 4 and 2 is 6, 4 and 3 is 7, 4 and 2 is 6. Of course, bring the decimal down and so on. So 3, 3, 6, 5, 3, 8, and 3 and 1 is 4. So very simply we add down and we subtract down also. And we also multiply that way. And we can divide too. So multiplication, division. And since we're dealing with floats, we can have this level of precision in our divisions. Now again, we've been doing it axis down, but we can actually change our axis. We can actually run, here's NA3, which is actually our own little array of 2 by 2. We can actually take this individual array here and we can actually add it across or down by using the axis equals. So we can also change how we do our work. So very, very, very powerful way. Remember now the default though is it does use down. It just takes them and stacks them and adds them down or multiplies them or divides them down. So, but we can change that with the axis equals option. Now an important thing to note here is all this previous work here, we've been dealing with arrays of the same shapes. A simple 1 by 2, right? 1 by 2, 1 by 2, and A1, A2. There's times when you have arrays that are of different shapes, and you need to work with them. And that's called broadcasting. Broadcasting is a way to work with arrays, to combine them or multiply, use mathematics with two arrays, different shapes. Now you could do this. Let's create one called X. This is a 3 by 4, right? 3 by 4 of 1 through 12. I'm going to create one called 101 here, called V. Simple 101. You notice the shape's different, right? This is just a one rank array. Now if I wanted to multiply this or add 101 to this, how can we do that? We couldn't do it normally because they're different shapes with the simple addition. Well, one way you can do it is you can create an empty, we're going to call it Y, and use the empty like. And we don't even have to know what it is. We can say just create something that's exactly like X. So, and it's just going to create it, and it's just going to throw random numbers inside there. It might do zeros, it might do, in this case, this huge value. Every time we do this, I think it's going to look different. The important thing is we created an empty array called Y. And we're actually in there, we're going to create a loop. So we know we need to do 4 ranks. So for each I in a range of 4, we're going to take Y and X, we're going to add V to it. And then we're going to print out Y. So now we can actually take this here. So you can see we took the X array and we added a 101. So 101 plus 123 is 224 and so on. Now this is definitely one way to do it. But the thing to note here is when you get very large arrays, and in this case this is a simple demonstration array, so a rank of 4 array is not going to cause any issues, but we're talking hundreds of thousands, very large arrays. This explicit looping can be very slow, and it's very computational. So it's actually a better way called stacking here. So take that same example. We have, we're going to create an array called VV, and we're going to tile it by 4.1. So we're taking V, and let's go and add print V here. We're going to print V. And we're in again here. So again, V was at 101. And we know we want to add this to X. Let's go and print X, right? So again, X is this 4 ranks. We have a 1 rank of V here. So again, we can't add this to this. What we can do is creating this stack called VV. Again, the name is what we want to call it, with the .tile command. I'm going to say, take this and create a stack of 4. So again, if I ran that, which I did right here, it took V and created a stack of 4. Now we have matching shapes. We can simply just add them as we saw before. No looping involved. So very simple. We take X and we add our new VV, which is our 4 stack, to create a rank 4 array of 101 from V, and add it to simple addition. So much easier than having to deal with looping. And the last thing here, of course, is we can also do things within our arrays. We saw before we can pull out slices. You can slice it, you can dice it, pull out elements, change elements. We can do additions, multiplications, lots of math. We can also pull out averages here. We can take this X array here, which is created, and we can say, what's the min, max, what's the mean we saw? So again, X of 1, 2, 3 to 12. Well, the max we saw in there was 12, the minimum was 1, and the average is 6.5. So we actually can do other mathematics with our arrays. Again, this is a simple 3x4 array, but imagine this was a 5,000 by 200 or some very large, huge arrays of data. To get this information quickly is very valuable in analysis. So NumPy, again, this is just the tip of the NumPy iceberg. Look at the textbook, there's a lot to it. And I'll leave you off with this last tip here. So as we've been looking at Jupyter Notebook, there is something called magic commands. And our first magic command here is history command. Magic commands start off with a % sign, and there's different references on different ones. We'll talk about .history. The % history command will just dump out everything we run in our notebook to a simple text block. I can copy and paste this. There's even our % history. I can copy and paste this so we can see everything we ran. And if you do -n, you actually get the numbers there too. In this case, block 15, and so on. So again, we don't get the output. We do see the elements that were in these blocks here. So here's this block right here. It's one of our last ones. You can see it right there, 132. So again, very valuable way to go back and just dump out or copy and paste everything that was in the notebook. So that's called your first magic command. And it's one of the really helpful tips that you can get from Jupyter Notebook. So that's all for a quick demo of NumPy. Hope this was helpful, and take care.